Welcome all my honors pre-calculus mathletes. We are going to be looking at expanding and condensing logarithms, but we are going to start this exploration by going back to something we already know. So we're going to think about the main rules of exponents in reverse. Why? Because exponents are the inverse of logarithms. So if we have a better foundation of the rules of exponents, we'll be able to better understand the rules of logarithms. That's the hope. So look at this example here. If the exponents are multiplied for terms with a common base, then, again, we're thinking about this in reverse, then the original problem could have been x to the fifth times x cubed. So what we're looking at, then the original bases were multiplied. Those original terms were multiplied. Then multiply the terms. If we are adding the exponents, then the terms with the like base were being multiplied. Let's look at the next example. Now we have 5 minus 3. The exponents were being subtracted. So hopefully you remember that means we must have had division. X to the fifth over x cubed. So then we divide the terms with the like bases. And just as a reminder, obviously you can probably see 5 minus 3 is 2, so this is x squared. Well, think about this problem. If I have x times x times x times x times x, that's x to the fifth, being divided by x times x times x, that's x cubed, then through the simplifying process, I know x divided by x equals 1. X divided by x equals 1, x divided by x equals 1. Oh, you're left with x times x, which, yes, that is in fact x squared. And then we have one more rule to investigate, and that's if the exponents are being multiplied. That is a multiplication symbol there. So then that means originally I had a base of x to the fifth being raised to another power. So if exponents are being multiplied of terms by an exponent value, then the original term was raised to another power. Exponent to an exponent. Do we remember these things? I sure hope so. But I'm going to illustrate this last one similar to what I just did in the 5 minus 3 problem. I know 5 times 3 is 15, x to the 15th power. But look at the way this is written, x to the 5th to the 3rd power. That is saying take x to the 5th and multiply it times itself 3 times. X to the 5th, x to the 5th. This brings us to the first rule. What I'm looking at right here goes back to this rule. Well, if you're multiplying like bases, terms with like bases, then I can rewrite this as x to the 5th plus the 5th plus the 5th power, and that is the exact same thing as x to the 15th power. Okay, but why are we doing this? You've already learned these rules in a past math class. We're going to use these to help us understand the rules for logarithms. So if I go to the next screen here, these are the properties of logarithms where a, the base is not equal to 1, okay? That's because 1 is the multiplicative identity. And n here can be any real number, okay? So that's the multiplier out in front, our scalar that we're looking at. And if u and v are positive real numbers. So these rules are really important here that are written at the top, that the u and the v, the argument of the logarithm, do remain positive. And we've looked at the graph of these logarithms already. So we know that there's a vertical asymptote, okay, on a non-translated logarithm function. So let's just analyze these rules, and you'll see they're pretty similar to what we just did with exponents. If we have multiplication happening inside the logarithm, that can be turned into addition of two separate logarithms, okay? So multiplication will move into addition in the expanded form. I'm going to be calling this a condensed form, one logarithm, and then there's expanded form. Now you see two logarithms. Okay, rule two, if you have division within one logarithm, so this is the condensed form, then you're going to have subtraction in the expanded form. Okay? This is the inverse of the rules of exponents. So then in step 3, I have the condensed form where inside the logarithm, I have the argument being raised to a power that can be rewritten as multiplication. This exponent is being brought outside in the expanded form. So before we apply these to other problems, let's investigate that these things are true. So let's look at problems that we should be able to evaluate and understand. So 2 log base 2 of 16, basically that's saying what power does 2 have to be raised to in order to get 16? So that is going to be 2 to the 4th power plus log base 2 to 8. What power does 2 have to be raised to get 8? That would be 3. So 4 plus 3 is 7. Well, what these rules are saying is that we don't have to do it as two separate logs. We can take this expanded form and we can condense it. We can condense this into log base 2 of 16 times 8. So this is equal to log base 2 of 128. Well, 2 raised to what power equals 128? That is in fact 7. So we get the answer of 7 regardless of which way we go. All right, so let's look at the second one where we have subtraction. So taking this expanded version and condensing it. So I'm going to start by condensing. So this is expanded. I'm going to move this into a condensed. So what do I mean by that? I'm going to take it and condense it into one logarithm instead of being two logarithms. And I can do this because they have the same base. Just like exponents, they have to have the same base. So I get log base 2, subtraction turns into division. 64 divided by 16. Okay, hopefully we know that that is 4. So I am actually trying to evaluate log base 2 of 4. Now, this is a lot easier to evaluate than the original expanded logarithms. 2 squared is 4, so I know that this logarithm is equal to 2. But let's maybe go the other way. If I think about the original logarithm in the expanded form, I know 2 to the 6th power is 64 minus log base 2 of 16. We just evaluated that on the other problem is 4. Well, 6 minus 4 equals 2. So we're confirming that, yes, these rules do in fact work out, and they'll work out for every logarithm. We've got one more, which we can expand. So here, this is the condensed version, where that 3, that exponent, is inside the logarithm. I'm going to expand it and move that exponent on the outside. So I get 3 times a log base 2 of 8. Okay, 3 times log base 2 of 8. If I evaluate that, which I already have, I know that that's cubed. 2 cubed is 8. So this is going to be a logarithm 2 base 8 equals 3. 3 times 3 is 9. Well, let's go the other way. Let's check this out. 8 cubed 8 cubed, if you have to put it in the calculator, no shame in that game, that equals 512. So now I've got to evaluate that or confirm how 512 can be written as a power of 2. Okay, so that is in fact 2 to the 9th power. 2 to the 9th power, 512 is 2 to the 9th power. So I then know, and maybe, you know what, I'm going to take a moment and just write it like this. 512, if I re-express it as a base of 2, that is 2 to the 9th power. Well, what if I used, I know I'm going off on a tangent. Sorry, it happens all the time if you're a student in my class. If I take this 9 and use the rule again, and I bring this out, I expand it into 9 times the log base 2 of 2. Hopefully you have learned enough about evaluating logarithms to know that a log base 2 of itself, 2, this is going to equal 1. That had to be a power of 1. So 9 times 1 is 9. A little bit of a tangent. Hopefully you're starting to believe these rules. We are going to be using them more in depth in class. Hope this was informative. Bring your notes to the next class. Have a good day.